Great. Okay, yeah, hello everyone, I'm Shuran and I come from Colombia. And today I'm going to talk about this topic called active scene understanding. Yeah, so just to give you a little bit background about my group in Colombia. So we typically do research in the intersection of computer vision and robotics. And also most of the time we try our best not to just do like them separately, and we try to kind of build a system that has both computer vision and robotics components. Where our goal is really try to develop algorithms that's able to kind of allow robots to see and understand their surrounding environment in a way that they can safely interact with this physical world. So across a lot of applications and systems that we have built, they often share a very similar high-level structure like this. Right, so where the system will typically start with some kind of sensory input that try to record the physical world in the form of images or videos. And then the computer vision algorithm will try to convert those kind of raw sensory inputs into a meaningful representation. And then that is used by the robotic system to plan actions such as grasping a coffee cup or walking around your home. So the process of extracting information about the environment from the raw sensory inputs is often referred as scene understanding in computer vision. And if you come with a robotics background, you're probably more familiar with the term of state estimation. So that's pretty much doing the same thing in the context of this talk. But depends on the application or the system that you're trying to build, the algorithm might choose to use different types of scene representations. Right? So here is just a few popular ones, such as 2D segmentation or 3D object detection or pose estimation. Right, so those are the type of representations that the algorithm can choose to use to represent the environment around the robot. So while these kind of algorithms and representations can be used for some applications, they actually share one fundamental limitation that I want to kind of highlight in this talk, which is the passive observer assumption, where the agents pretty much just sit there and try to record an image or video without the ability to actively interact with the environment. So all the action actually happens after they actually already extract this kind of scene representation. So this assumption is called passive observer assumption, and it's actually kind of widely reflected in many of the standard benchmarks for computer vision, which contains only static images captured from a third-person view. Right, so the typical ImageNet or Pascal VOC dataset, they all kind of following the same protocol. And even for the datasets that's recently come up with that's focused on video understanding, they're still missing some critical information that's able to associate the motions in the video with the interactions or the action that's performed by the agents. So for example, since the system is not able to actively choose or apply its own action, this kind of data set will not allow the agent to fully understand the causal relationship between the action and the motion observed in video, and therefore prevent it from achieving deeper understanding about the environment. However, on the other hand, we know that we as humans are actually really good at using our own actions in order to retrieve useful information about the environment. So here are just a few very simple examples, right? So for example, before we jump into a pool, we may dip our toes first into the water just to sense the temperature of the water before we commit it to swim. And similarly, before we try to lift up a big box, we may try to push it first in order to sense its weight. And similarly, in the morning, in order to find a t-shirt from a pile of laundry, you may try to pick it up in order to recognize it, right? So in all these kind of examples, we use a very different action, such as dipping, pushing, or lifting, in order to retrieve the relevant information about the environment, such as the temperature of the water, the weight of the box, or the identity of the cloth. And ultimately, what we do is that we can use all this information in order to plan our future actions, such as whether we want to swim in the pool, lift out the box, or wear the t-shirt. So the question that we want to ask is whether we can enable the robots to share a similar capability. So we refer to this goal as active scene understanding, which means that use the active action or interaction to retrieve information about the environment. So the plan for today is that I'm going to use some of our recent projects to demonstrate the idea of active scene understanding, and more importantly, its advantage over this kind of classical passive vision paradigm. And I will mostly focus on kind of like the high-level ideas and leave out some of the details of implementation, but happy to answer questions in the end. So first, and also most obvious advantage for active scene understanding is that by using active interactions, the agent now has opportunity to obtain some additional observations about the environment that is otherwise hard to obtain passively. So one good example of how we can leverage this advantage is when we try to deal with deformable objects like cloth. Right, so due to their deformation and scene geometry structure, cloths often experience the most extreme case of self-occlusion, especially when they are folded or crumpled together, which can make the perception task extremely difficult. So therefore, instead of trying to kind of directly estimate the cloth configuration under arbitrary states like what we show on the left, what we can do is that we can use a very simple robot action to transform the cloth into a state that is more trackable for perception algorithm. So what we do is we just ask the robot to pick up the cloth from wherever it can. And by using this very simple pickup action, the system is able to reveal more surface area on the garment by leveraging the gravity force. Basically, the gravity pulls the cloth down, and therefore you can see more surface on the cloth. And also at the same time, this kind of pickup action itself is very simple and does not rely on much prior knowledge about the cloth or its pose, which means that it can be executed very robustly with very high success rate. Therefore, we can feel very comfortable to add this kind of interaction before the perception algorithm. So with the help of such simple interaction, we are able to develop a perception algorithm that's able to infer the full 3D geometry and configuration of an unknown garment. And then in a follow-up project, we take this idea one step further and then develop a robotic system that is able to actively unfold the cloth using a sequence of dynamic actions. So in particular, we use the action fling in order to unfold the cloth. So here is the resulting system that we call it FlingBot. So you can see that in the end of the interaction sequence, the system is able to kind of reveal many key features on the cloth that is originally hidden in the initial observation, and therefore kind of like significantly simplifies the later perception and planning algorithm. And then, so apart from kind of increasing the object's visibility, surface visibility, active interaction can also help the system to develop the objects, to kind of understand the object's physical properties that goes beyond their visual appearance. So physical properties like mass and friction, we often know that it's actually not directly observable from the appearance. Right? So that's actually why learning physical properties through vision data is actually quite a very challenging task. Right, so one obvious reason is that most of those properties or attributes are not directly observable from appearance or from visual data alone. So for example, here it's two very different metal made with very different materials, has different density, but their appearance looks very similar. And a more subtle reason that's why it is hard from estimating physical properties from vision is that even if we use interactions, but if the interaction is quasi-static, the physical property will still be hard to observe. Right? So here in this example video, we actually push these two blocks, each of the blocks with very different weight and friction. But in the end of the interaction, both of them stop in the same location because we use this very slow quasi-static pushing. So from the vision data alone, we kind of cannot really see obvious difference. Therefore, it's very hard for us to reason about their underlying physical properties. And also, objects' motion under interaction is often influenced by multiple physical properties. Right? So given the same initial momentum, the sliding distance of an object is determined by both its friction and the friction coefficient and mass. Therefore, in order for the system to really decouple this different physical property, it really requires the system to simultaneously reason about all of them in order to decouple those properties. So to address all this challenge, we developed an algorithm called DensePhysNet, where the key idea is to learn a prediction model that is able to predict the future state of the object given the current observation and a robot action. So our hypothesis is very simple. Basically, in order for the algorithm to accurately predict the future state, the system will need to acquire an implicit understanding of objects' physical properties and how they will influence object motion. Right, so as a result, the system can learn about object property without explicitly supervised on those parameters. But of course, in order for the network to really learn about the physical property, we need to be careful about the action selection. Again, quasi-static interaction will not give us enough information. So to do that, we actually designed two types of dynamic interaction, which is sliding and collision. So here is actually how the robot executes those kind of actions. And then here is actually the system in action, where the robots will interact three different objects made with different materials. So on the left, on the right, we show the feature embeddings for all the pixels, where the color indicates the object instances, where the larger distance on this plot indicates larger feature distance. So we can see that initially, all these three objects is not really distinguishable on the feature space. However, after a few interaction steps, the feature vectors will be started gradually separated in the embedding space, which indicate that they start to encode object physical attributes. So here, the robot, again, is using two types of interactions, sliding and collision. Yeah, so, and if we train a linear classifier on top of the learned feature, we can actually decode the accurate physical parameters, such as friction and mass. So here's the decoding error for the system. Basically, yeah, so on this plot is showing the decoding errors when the system is using different actions, such as sliding and collision. And in comparison, we can see that basically using both interaction will help the system to learn a more accurate physical representation. So a natural question here is, what if we introduce different type of actions? Will that help the system to learn an even richer representation? Right, so to answer that question, we actually looked into another type of dynamic action, which is tossing. So the goal of the system is it's trying to learn how to accurately throw any given objects into a target location. And the question we are interested to answer here is, what kind of information about objects can the system acquire in the process of learning how to throw? So in other words, what does the TossingBot need to learn? Right, so first, we observe that the system needs to understand the object's mass distribution. Right, so for example, given the screwdriver, if the robot grasps and tosses the object near the center of mass, then it would land much closer than grasping it from the tip. And in addition, the system also needs to understand the object's aerodynamics. So for example, a ping pong ball would land much closer due to air resistance. So by learning how to throw different objects, TossingBot is able to kind of acquire an object representation that encodes object properties, such as their mass distribution or aerodynamics, which are all the information necessary for the system to accurately throw different objects. And more importantly, the system is able to learn all this information without any explicit supervision. So that's actually leads us to the final advantage of active scene understanding, which is that it provides a new opportunity for self-supervised learning in robotics. So as we know, training machine learning model often requires labeled data, and oftentimes the most expensive part of training a neural network is to get ground truth label with human annotation. However, in the active scene understanding framework, the system is now able to kind of automatically collect its own training data by applying its own actions in the environment and observe the future state of the environment as a ground truth label. And actually, for most of the projects that I talked about today, have already used this idea of self-supervised learning. Right, so for example, in DensePhysNet, the algorithm is trained to predict the future state of the block after applying the action. And by observing the actual object movements in the real world, the system can automatically obtain the ground truth labels for this prediction. And similarly, in TossingBot, the robot is able to track the object's landing location with a top-down camera and use that as a supervision signal to train the whole system. So eventually, when the robot finish toss all the objects in the bin, the robot will actually automatically reset the state in order to continue the training. So as a result, the system can continuously gather training data overnight without human intervention. So to summarize, in today's talk, I try to highlight 3 main advantages for active scene understanding, as it can help the system to obtain additional observations that is hard to obtain passively, or discover the object's physical properties beyond their visual appearance. And finally, it's able to provide new opportunities for self-supervised learning in robotics. And that's the end of my talk. And I hope that by kind of introducing this idea of active scene understanding, we can change the role of computer vision from more like a passive observer to like kind of just sit there and try to understand images to an active explorer that can constantly engage with the environment in order to continuously improve their understanding of the world. And that's the end. Thank you for listening, and I'm happy to answer questions.
Okay, yeah, thank you.